everybody. We're going to get started here. Thank you all for coming to the seminar today. It is my great pleasure to introduce Julia Shates, who is talking about her master's thesis work. And Julia and I have been working together about 1.5 years now on this work that we've been doing in Scandinavia. I wanted to give you guys some background about Julia in case you didn't know, things I've learned about her. So before coming to University of Wisconsin, she got her undergraduate degrees at University of California, Irvine. She's a Californian through and through. So am I. It's kind of like you're not supposed to admit you're Californian, but no. So she got degrees in both Earth System Science and she got a degree in Spanish. She worked, while she was at Irvine, she worked with Dr. Gudrun Magnusdotter, who has been here to give a talk before, so some of you might be familiar with her work. During her undergraduate, she did an NSF-funded REU at Colorado State with Dr. Elizabeth Barnes. Between undergrad and graduate school, Julia did several educational opportunities, including being an outdoor science educator. And in addition to that, she's attended herself as a student and I think maybe as a teacher coming up these international Arctic research programs in part Arctic Summer Field School, both in Barrow, Alaska and...
there was one in Barrow, Alaska, and there was one in Fairbanks, Alaska, and then maybe future one in Yukon.
In the Yukon.
Yeah.
Great. Yeah. So, and then recent news, Julia applied for an NSF graduate fellowship and was awarded an honorable mention. We just found out about that recently, which is great. And a fun fact about Julia, she knows a lot of languages, and one of them is Russian, which is great for me because when I butcher the names of Russian scientists, who happen to be a lot of Russians do radar science, Julia can say the names like very elegantly, like Matrosov, which is actually, and then Irina Gordiskaya. Yeah, so much better than mine, which is terrible. Yeah, so some of those will come up. So I am very pleased to introduce her work on high latitude precipitation, characterizing snowfall regimes, and identifying key processes at 2 distinct Scandinavian sites.
Thank you so much, Claire. So to begin the talk, I'll go through an outline. I'm going to start with introducing the importance of snowfall, and then also the difficulty of observing snowfall in high latitudes and also in general. Then I'll go through the measurement sites, the instrument suite, and the data that I'll be using to study snowfall processes. Then from there I'll go into the methods, and then results, which has 3 sections, part climatological, the snowfall events themselves. Then I'll compare the different sites in the snowfall at these 2 distinct Scandinavian sites, and then I'll conclude and go on to some future directions. So, starting with intro. Snowfall is important because of the role it plays in the hydrologic cycle. It leads to, in surface mass balance, it allows for accumulation of snowpack over glaciers and growth of glaciers, and also snowpack accumulation in mountains. And this is important for humans in particular because we depend on mountain snowpack for water resources in many parts of the world, mid-latitude and high latitude. And in Scandinavia in particular, they depend on snowpack and waterfalls for hydropower. So Norway is 95% hydropower for electricity, and Sweden is 65%. So this figure here just shows the number of hydropower stations in Scandinavia. And in southwestern Norway, there's the largest hydropower reservoir. This is Blåsjø Reservoir. And I just wanted to show that it's contained by at least 11 dams. So precipitation in the high Arctic and in mid-latitudes and all over the world are important, but they're potentially changing. So with warming winter surface temperatures, there's an uncertain future for snowfall. There's projected increases in high latitude precipitation, but research is suggesting there could be a shift from snow to rainy regimes. So I'm showing this figure here from one paper of Tanya and Andrew, and it's the trend in model mean snowfall fraction. So I just want to point out that in this region, right here is Scandinavia, and there's a decreasing trend in snowfall over this region. So this would have severe impacts on economy and water resources, spring flooding, ecosystems, and the permafrost in the region. And even current day, there's been an increase in noticeable rain on snow events in midwinter, which leads to refreezing within the snowpack. And this has implications for people and animals that depend on getting to food sources underneath these ice lenses that develop. So one of the sites that we'll be talking about today is Kiruna, and even local news sources are pointing out how quickly it's warming. So these are just some headlines I wanted to show. So northern Swedish cities seeing the effects of climate change, so the warming. So snowfall is important, but it's really difficult to observe. And in the high latitudes, we have this really vast region, and it's sparsely populated. So we have not very many measurements in this high vast region, and that's exacerbated by challenges in measuring and observing snowfall. So the cold conditions lead to instruments struggling with the icy harsh cold, and then wind has serious impacts on snow. So even if you're in this building during a snowfall event, you can look outside and see how the snow is impacted by wind. So you have some places where you can see snow is just falling, and some it's just completely moving upwards. So wind really impacts snow. And in addition to that, as it falls, it's not falling in this nice even sheet. It's falling, some places there's more accumulation than others. So these lead to some challenges. I have a figure here that I'd like to point out. This is a figure of a double fence around a precipitation gauge. So you have two fences around a gauge, and this is to try and slow down the wind precipitation. So this is a method used to try and improve our ability to capture snowfall. And this figure right above it is the difference in using just a single fence and a double fence. So you can see the double fence, which is in red, captures a lot more snowfall than just a single fence. So those are some challenges there. And then, in addition, there's been efforts using remote sensing to capture snowfall and observe it, but with ground-based radar and space-based observations, there are a lot of deficiencies actually observing what's near the surface. So despite these challenges in observing and measuring snowfall, there's been some recent research on snowfall in mid and high latitudes. So Noren et al. Looked at snowfall sensitivity in Sweden to larger scale circulation patterns in weather states. And then Pettersson et al. And Poole et al. Are looking at snowfall in Marquette, and they identify snowfall modes, so like lake effect snow and deep synoptic snowfall. Shirley et al. Study snowfall and accumulation in Haukeliseter, Norway, which is one of our sites I'll describe soon. And that's, I'll go to that. And then Savrains and Gordetska et al., they study surface mass balance over Antarctica so these three studies are using a radar that I'll be describing actually using for this research. So their studies are similar to mine in that we're using this radar and reanalyses to infer what's going on with the snowfall in these sites. So what are my motivating research questions for this project? First, I want to see how are snowfall events influenced by their environment, and how do synoptic scale weather patterns and topography influence the type of snowfall in a region? And can we identify or speculate upon physical mechanisms influencing distinct snowfall regimes? And then once we answer those questions, or try to, I'm curious to know, how do snowfall regimes vary across distinct regions in the high latitudes? And how are the snowfall patterns and physical mechanisms unique to those areas? So moving on to look at our measurement sites, the instrument suite, and the data from there. The region that I'm focused on is Scandinavia, and so I have it circled here. And this region is relatively warm for its high latitude position, and that's attributed to the ocean circulation with the Gulf Stream bringing up warmer waters and keeping the area more moderate. And then this region is also impacted by frequent extratropical storms, and the terrain includes both mountains, mountain fjords, and permafrost. So our two sites are here on this map, Haukeliseter, Norway, and Kiruna, Sweden. And I'm including here their temperature, the box and whisker plot to illustrate the temperature distribution for their winter months. So on the y-axis, you see we have degrees Celsius, and on the x-axis is each month in winter that I've defined. So in Haukeliseter, the boxes are in yellow, and in Kiruna, we see them in blue. So for Haukeliseter, we can see, also something I want to point out is that dashed line is the mean temperature for, this is November through April, 1979 through 2018. It's ERA 5 2-meter temperature. So we can see that Kiruna, Sweden has colder temperatures in the winter than Haukeliseter, but both of them we'd expect to see winter solid precipitation. So for some context also, how far away are these sites from each other? They're about 1,000 kilometers, and I like to think about that as California, driving from San Diego all the way to Oregon. So that's something to keep in context. How far away are they from each other? So our first site, Haukeliseter, Norway. We had instruments at this site from October 2016 to June 2017, and this site is unique in that it is very high, so it's subarctic, it's not quite in the Arctic, it's high latitude, and it is in this mountainous region where directly west of it we have these mountain fjords. And these mountain fjords right here, so these fjords, these are sea level, and this is 991 meters above sea level. So in this, this tiny distance is extreme topography to get up this high. And we see a lot of snow in this region, high wind speeds, and there's also snowfall that occurs outside of winter time. Our second site, Kiruna, Sweden, is in the Arctic. It is colder, as we saw also in the Era 5 temperatures. It's defined by having lower wind speeds, snowy winter, it's dry and it's cold. And in this region, so here's Kiruna, and in this region it's similar topography to northern Wisconsin in that we see scarring and remnants of when there were glaciers over this time in the last ice age. So that's similar terrain in that area. This area, however, is very different terrain from northern Wisconsin. These are the highest mountains in Sweden. So directly west of Kiruna, we see these mountains. Also not low elevation here, so 530 meters above the surface. So the instruments we had at these sites. At both sites, we're measuring wind speed and direction, and temperature, and we have relative humidity, but only at Kiruna. We get our measurements from different institutions. In Haukeliseter, we have snow accumulation from a double fence around a precipitation gauge, and so this is our double fence. And this double fence complies with a few standards for measuring precipitation, and particularly solid precipitation. Our next instrument is the micro rain radar, which I've hinted at a little bit before. So here's our radar, and it's a vertically profiling radar. It's K-band. It's small and it's portable, so you can see it's just on this little balcony here. It's originally developed for precipitation measurements on the buoys on the North Sea, and it's not affected by sea spray, so it's only sensitive to larger hydrometeors, and it does not see clouds. It's not sensitive to clouds. In order to use this radar to study snowfall, we use a processing method of the Doppler spectra to get effective radar reflectivity, Doppler velocity, and spectral width. Now, before I continue on, we're going to take a sidestep and do a little bit of micro rain radar 101. So what does the data look like that I'll be studying to introduce you a little bit first? So we have here height, so we're looking at a profile. So every time step that we're looking at is the precipitation falling down towards the radar. So we have height above the surface on the y-axis and time on the x-axis. The radar reflectivity here in color represents how we can infer from the radar reflectivity, if it's a large dBz value or a small one, how many and how small or large are the particles detected by the radar. And then from there we can make some assumptions about and some calculations to gather how much liquid water equivalent is associated with that snowfall event. The next variable that I'll be looking at for this study is the Doppler velocity. So again, we have the y-axis is height above the surface, and then time along the x-axis. And for our Doppler velocity, we're looking at the terminal fall speed of hydrometeors, and also that includes the motion of the air in the Doppler velocity. A positive velocity indicates motion towards the radar, whereas a negative velocity is movement away from the radar. Going on to the rest of our data, I'll be using Era 5 reanalyses in order to get synoptic scale context surrounding these events. The temporal resolution of this data is hourly, and spatially we're looking at 0.25 by 0.25 degree grid. And something to consider is that as we get higher latitudes, we're getting finer spatial resolution. In this figure here, I've plotted latitude, longitude near the field site just to see, what we have for the ERA 5 reanalyses, how close are they to the actual site. So this is just what I have here plotted. They're superimposed on each other, the actual site, latitude, longitude, and the ERA 5. So I've given you an idea of the introduction of snowfall, measurement sites, and instrument sweeping data, and now I'm going to tell you a little bit about my methods in doing this study. So first, I'm starting with high latitude winter. I've already sort of hinted that I'll be only looking at November through April, even though we had instruments for a little bit longer out there. And using the radar, I'm using a threshold on the reflectivity to identify when is there precipitation occurring. And this radar reflectivity that I'm looking at is 300 meters above ground in order to avoid ground clutter that the radar might pick up. So we get precipitation occurrence using that. Having this precipitation occurrence, I'm going to compare observations in ERA 5 to see what are the temperature and winds like during the precipitation events in general. Yes?
Do you establish that threshold, Julia, by observations?
So that is the minimum detectable reflectivity that the radar sees in order to actually identify that there is some kind of hydrometeor.
Okay,
Yep.
okay.
So that's, it's just a sensitivity thing.
Okay.
Yeah. So then after looking at precipitation occurrence, I want to look at those specific events. And these events must last, are defined that they last at least 3 hours, and they're separated by 6 hours at least. Then we'll do case studies to specifically answer the questions that I brought up at the beginning of the talk. So moving on to these results. So climatological. So this plot I've shown you a little earlier in this plot already, or in this presentation already. Well, what were the months there? What were the months like when we were there with instruments? So each black star overlaid on this plot represents what the mean temperature was like during the month of deployment. So for the most part, we can see that the month that we were there with instruments, it's within the expected climatology for temperature. And the only one that really stands out as being different is this December in Haukeliseter. I mentioned it before, but I do want to point out again that yellow is Haukeliseter and blue is Kiruna, Sweden. So this particular December in Haukeliseter was warm compared to the climatology. So comparing surface observations and ERA 5 reanalyses. So this is the temperature distribution during precipitation events. So that's when we have radar reflectivity values above -10 dBz. So we have a new box here, and these boxes, we have this yellow chiffon for Haukeliseter ERA 5, 2 meter temperature, and this golden color is the surface observations. So for the most part, we're seeing that the ERA 5 reanalyses are capturing trends that are actually happening at the surface. Although for a few of the months, we're seeing that the surface observations have a slightly warmer distribution during precipitation events. In Kiruna, Sweden, so this light blue is the ERA 5 surface temperature, and the darker blue is the surface observation. So we're seeing, one, it's capturing generally the trends we'd expect for it's cold and really cold in February, we have these cold months. But for the most part, our surface observations are actually colder than what yes?
Sorry to interrupt. The question I have is about the temperatures. Do you know what the error location was in terms of the altitude of the state, the point where you're getting that 2 meter temperature?
For the 2 meter
Did that impact
temperature?
the temperature if you have inversions or?
Oh, so we'll be looking at the vertical profiles during events later in this talk. So
Yeah, but more the what you see at the closest grid point, I guess.
right.
That elevation compared to what the actual elevation of your station is.
So I would need to just double check and look into things further before answering that, but I can get to you about that. Yeah. I don't want to say a wrong number, Okay, so moving on to the winds. So on the left column, so this is for Haukeliseter, by the way. So on the left column, we're seeing surface winds during winter precipitation, and on the right panel, we're seeing ERA 5 10-meter winds during winter precipitation. So some things that stand out, I do want to point out, this wind rose, so all the wind roses that I'll be showing are giving us an indication of where the winds are coming from, how strong they are, and how dominant are those winds during this type of, this season, this winter precipitation. So this would be showing us that we have, at the surface, we have a lot of westerly winds that are very strong. So the colors are how strong they are. Whereas we have winds coming from the southeast that are lighter wind speeds or weaker wind speeds, but this is still a dominant mode. But in the ERA 5 reanalyses, we're seeing that we're not capturing these high winds at Haukeliseter, and we're not capturing at all, basically, this southeasterly wind mode. So we know that with reanalyses, it's hard to capture some details because of the mountains in the region, and this region has some very extreme topography. So this isn't surprising to see that reanalyses are having a difficult time capturing these winds. So in Kiruna, we're seeing that we have two dominant wind modes at the surface. So we have this northerly wind mode and the southeasterly wind mode primarily. The ERA 5 reanalyses do a generally good job capturing that. However, something I did notice is that there are no southeasterly winds at all, and there are some southwesterly winds at all in the ERA 5 reanalyses, whereas we do see some southwesterly winds at the surface. We'll see why it's important a little here. Okay, so we've kind of discussed what are the wintertime precipitation climatology of the events, and moving on to the actual events themselves. So events that last at least 3 hours, there were 55 events that we found using the radar reflectivity threshold in Haukeliseter, and 59 in Kiruna. And I'm about to go into some case studies and the methods that I use to specifically explore the case studies, but I want to point out right now that for these case studies, I've handpicked, so, I've selected case studies that represent what precipitation through the radar looks like. So these are the main types that I've identified qualitatively, and I'll go through those soon. Yep. So with each case, we're going to look at the radar observations. And with the radar observations, I'm asking some very specific questions to learn about this precipitation. So do we see that it's deep or shallow in the precipitation profile? Are the radar reflectivities, in dBz, small or large? Does the precipitation look like it's continuous, or is it stopping and going? Is it intermittent? And also, are the particles moving away or towards the radar? Once we've looked at that, I'm curious about the meteorological surface observations. So where are the winds coming from? I'm very interested in these winds and what that implies. Are the winds going over this extreme topography or a gentle upslope? What are the winds, or what are the conditions during the event in terms of the temperature and relative humidity? And how much accumulation are we getting at the surface? Then, revisiting those ERA 5 reanalyses, what are the synoptic scale conditions associated with the event? And what is the vertical structure of the atmosphere around the event? So going on to our first case. So I have here an animation of the mean sea level pressure, and that's in the color. We have mean sea level pressure superimposed with geopotential height contours. This is our first event. It lasts over 48 hours, and we have liquid water equivalent accumulation of 23.86 millimeters. And this is what I'm defining as a deep snowfall event. So what does that look like in the radar? Oh, something I do want to point out. So I have an arrow indicating where our site is, and we have a weak low pressure system developing south of the site. So this is what it looks like in our radar. So we have our height and our time, and we're seeing relatively high rate of reflectivity in the 20s and maybe approaching higher, and we're seeing a precipitation that looks relatively continuous. So what I'm going to do with this data is I'm going to take it and I'm going to compress it into a 2D histogram, and this 2D histogram removes the element of time. So we have our height on the y-axis and our radar reflectivity on the x-axis, and this color represents the normalized count. So when we have a very dark purple color, it would suggest we have a lot of observations at that height and for that reflectivity. So for this deep snowfall event, we're seeing a defined structure and increase in radar reflectivity down the column. With an increase in radar reflectivity, again, we're thinking about, is this more particles or larger particles? Those are some of the questions that we want to think about as we're looking at that increase in radar reflectivity. Then, with our Doppler velocity, we're seeing most of the particles are falling towards the radar with a few little blips of maybe upward motion. And we're going to for this radar information, we're going to compress it again down into a histogram. So now, though, we have our height again, and we have Doppler velocity on the x-axis. And the colors, so the lighter yellow, will represent more counts for that height and at that velocity. So you can see, if you squint your eyes maybe, that there is an increase in Doppler velocity as you get closer down to closer down the column, or closer to the surface. So that would also maybe suggest and support that the particles are aggregating and getting larger and heavier as they fall towards the radar. So I mentioned that we'll be looking at the meteorological observations. So this event has cold surface temperatures and southeasterly winds. I don't think I mentioned, but I wish I had, and I'll tell you now, that at Haukeliseter, southeast of our site, we actually have a gentle upslope. So it's not flat, it's not extreme topography, but we do have a gentle upslope coming up towards the site. So that's what defines this snowfall event. Now I mentioned we'll be looking at vertical profiles. So the left panel has the before the event, the center panel is an hour during the event, and the right panel is after the event. So in the orange line, we have temperature, and in the blue line, we have relative humidity. And I just want to point out that something striking for this event is we have high relative humidity through the boundary layer and into the free atmosphere during this deep snowfall event. And before and after the event, we have a temperature inversion, and also we have some relative humidity inversions in the atmosphere. All right. So for our next case, the next type of snowfall we see in Haukeliseter is pretty long lasting. It's over 35 hours with very little liquid water equivalent accumulated at the surface. And for this event, we have a persistent high pressure sitting over the region. So what does a snowfall look like during these conditions? So it's quite different. So we're seeing, so going right into that histogram, because that's where we're going to see that summarized, is this event is very shallow, and the highest reflectivities are near the surface, and they're pretty high radar reflectivities too, approaching 10 dBz. So this is different from our deep snowfall event. So moving into our Doppler velocity, this is also distinct. This is confirming, yes, we're seeing a shallow event, and we're seeing some blues, and so upward motions. And looking at this histogram, we're seeing, yeah, we have these updrafts, upward movement, up to -1 meters per second in the Doppler velocity. So during this event, it's cold, and it gets colder. And it's also associated with that southeasterly winds and upwards, gentle upslope motion. And during this event, so again, this is before, during, and after, we're seeing a strengthening temperature inversion, and also it's like the relative humidity is it's just within the boundary layer. It's very dry in the free atmosphere. So this next event is Extreme Storm Erd, and this event lasted, it's actually named that, and it lasted over 130 hours, liquid water equivalent accumulation of 117.78 millimeters, and there were several low pressure systems hitting the coast of Scandinavia, so several of those. And there were hurricane force winds along the coast of Norway as well. So like reaching 70 knots. It was a very extreme storm. So I'm defining this event as pulsed, and I'll show you why. So this is a picture found on Twitter, of Extreme Storm Erd. It's pretty extreme, very. Okay, so here's our pulsed snowfall event. We have a really deep along the column, and it's long lasting, so we know it's over 130 hours. And this looks very different from our deep case, which was also deep. So this is what that first case looked like that I showed you, and this is what this one looks like. So it's very distinct. So let's zoom in a little bit to see how different this really looks. So I'm going to zoom in just for these 16 hours. And you can see how pulsed this precipitation is. We have very high radar reflectivities, and it's on and off. So as that question, is this intermittent snowfall? Does it pulse? This is what I'm talking about. So this is that histogram again, so that height and radar reflectivities. And this is very different from the other histograms I've showed you. We're seeing a broad range of radar reflectivities throughout the column, and we have very high radar reflectivities near the surface, so reaching 25 dBz and potentially more. Looking at the Doppler velocity, we're seeing that we have downward motion toward the radar and also some upward motion, and that kind of fits in with this pulsed category that I'm telling you about. So we have broad velocity, Doppler velocity throughout the column, and we have updrafts in the velocity. So we're seeing -1, -0.5 meters per second of how quickly they're moving up. Throughout this event, we're seeing near freezing temperatures. So this is relatively warm compared to the other cases we looked at. And we also see that there's temperatures that exceed this 2 degrees Celsius, which is our threshold for rain and snow, actually. This event is associated with westerly winds, and recall that extreme topography of the mountain fjords. So think and how that relates to the pulse nature of this storm. So we have high relative humidity through the boundary layer and free atmosphere through this event. There are no temperature inversions associated with the event, and also we're seeing those warmer temperatures captured by in this vertical temperature profile at the surface. All right, so here's a summary of the types of events I've shown you in these cases that I'm hopefully going to define as regimes. So we have deep events that are long-lasting. This one was over 48 hours. Liquid water equivalent accumulation was substantial with 23.86 millimeters, defined with high radar reflectivity, a structure in the 2D histogram, narrow Doppler velocities, so generally staying kind of not broad the way we saw with the pulsed. We had the southeasterly winds. It was a cold event, the moistening of the boundary layer in the free atmosphere through the event, and there was that weak low pressure system we saw south of Norway. For our shallow event, it was also long-lived. It had a duration of over 35 hours, 4.28 millimeters for accumulation, and lower radar reflectivities and broad Doppler velocities, which we can infer something about the possibility of turbulence happening within that boundary layer. Again, we saw southeasterly winds, just like the deep event, and we saw it was very cold. Throughout the event, in the vertical profile, we saw a strengthening of the temperature and relative humidity inversion, and there was that persistent high pressure system sitting over that region. For our extreme storm our pulsed event, it was very long, several days, 130.8 hours. A lot of liquid water equivalent accumulation of 117.78 millimeters. High radar reflectivities and very broad Doppler velocities throughout the column, so inferring something about the turbulence and the updrafts. We had westerly winds, and it was warm during this event. Similar to the deep case, we saw moistening of the boundary layer in the free atmosphere, and there was a very deep low pressure system associated with this event. So moving on to Kiruna, so we're now going into the Arctic region. We also see deep snowfall cases. This particular event that I'm showing you lasted about 20 hours, 20.51 hours. Liquid water equivalent of 5.12 millimeters. And similarly, we have a weak low pressure system over our region. So we have a similar looking figure for a deep snowfall. And looking at the histogram, we can see again that we have this defined structure in the histogram where it's actually even more of a narrow range and reflectivity along the column. And we also see that increase in radar reflectivity down the column. Looking at the Doppler velocity, it's basically invariant. We're seeing that there's a lot of particles falling right towards the radar. It's calmer looking. And same with the Doppler velocity, it's showing us it's invariant. You're seeing most of the particles are falling around 1 meter per second. And there is a large, if you squint your eyes, Doppler velocity increase closer to the surface. So we can infer something about potentially particles growing and aggregating and getting heavier. So during this event, we had cold surface temperatures and northerly winds. And with those northerly winds, something I'd like to infer is maybe the potential source of moisture, being brought to this snowfall event in this region. So for our vertical profiles, there's high relative humidity through the boundary layer and the free atmosphere during the event. That's something I want to point out like that. For our next shallow snowfall case, which is also a shallow case in Kiruna, we see a similar feature in that we have a persistent high pressure system sitting over the region. This event lasts a very long time, of 40.38 hours, and very little liquid water equivalent accumulation for this event, so it's 2.53 millimeters. So this is what I mean by shallow. So, recall the radar can't see clouds, so this is just hydrometeors falling towards the radar. And we see that, yes, it's very shallow in our 2D histogram. We can confirm that. And we have low reflectivities for this event. So this would imply some information about the particle sizes being smaller and also maybe fewer particles. So those are some uncertainties also with the radar. With our Doppler velocity, we're seeing, for the most part, particles are falling lightly towards the radar. And this histogram is showing, yes, very invariant Doppler velocity around 0.5 meters per second. And very, it's not varying very much at all. During this event, it starts out cold, so starting out at negative 14 degrees Celsius and getting even colder. And it starts out not that humid and even getting drier. With this event, we have northerly winds associated with the event, and something I'd like to point out, especially with this high pressure system sitting over the region, is the potential for cold air advection from the north. For the vertical profile of this event, we have a pronounced temperature inversion and relative humidity staying moist only within this boundary layer and very dry in the free atmosphere during, before, and after the event. This next storm looks similar to this giant case we saw for Storm Erd, although it's not 130 hours, it's 76.3 hours, and I'm defining this one as intermittent snowfall, and I'll show you why. There was a substantial amount of liquid water equivalent accumulated at the site, and this deep low pressure system. So this might look similar. So we have pulse-looking precipitation, but I'm just calling it intermittent. It's on and off precipitation, and in the 2D histogram, we're seeing this broad spread of radar reflectivities throughout the column. So we don't have that refined structure that we saw for our deep snowfall events. Now you might be thinking, Julia, that looks like the pulse case, and I'll tell you no. The Doppler velocities are, for the most part, falling downwards. We don't have any upward motions and no negative values for Doppler velocity. And if I show you the histogram of it, it's showing that we have a large increase in broadening in Doppler velocity near the surface, but we're not seeing any of those upward motions that would suggest some kind of turbulent air. So this is different from pulse, which is why it got its name as intermittent. So it starts out cold and dry, and we have an increase in temperature and relative humidity through the event. And this event is associated with the southeasterly winds, which is the most common mode for winds for precipitation in this region. The topography it's going through is not extreme, so we wouldn't expect to see some kind of pulsed precipitation the same way we see at Haukeliseter for pulse events. So we have a weakening temperature inversion throughout the event. So we start with an inversion and then it dissipates, goes away. And something I'd like to point out is the temperature in this profile shows that we have, in the vertical, some temperatures that correspond to the dendritic growth zone, which is a temperature range of -10 to -20 that promotes growth of snow. So for our final case, I'll be showing you a little bit of snow virga that the radar detected. Now, this case is relatively short, much shorter than the other cases I've showed you. It's only 3.2 hours and very little liquid water equivalent accumulated at the surface. And we have a low pressure system north of Scandinavia. Here's Kiruna, there's no arrow. Okay. Surprise, we have very high radar reflectivities aloft, and we have regions of no radar reflectivity closer to the surface, or very low radar reflectivities close to the surface. So with that, this suggests, so let me show you the histogram, because that's even more striking. So again, more and higher radar reflectivities higher up in the profile. And as you go down the column, you're seeing a decrease in reflectivity as you get close to the surface. So this would be suggesting that as the particles are falling, they're being affected by dry air and they're evaporating. So we're seeing snow virga. Now let's look at the Doppler velocity. Maybe we have some turbulence or something. Nope. We have fall speeds that are coming towards the radar and very quickly. So getting near this, 2 meters per second, and they're falling towards the radar very quickly. So we have a broad Doppler velocity, not really any structure or any increases that, maybe some people might start squinting and seeing stuff, but Generally it's broad, but we're not seeing upward motion in this negative Doppler velocity range. So I mentioned, so let me just go back for a second. I mentioned earlier that both ground-based radar and satellites have a hard time seeing the surface, and this is kind of highlighting one of those points that we would consider is what is actually happening at the surface. Because, you know, there's not anything being accumulated, but aloft we have reflectivities that are associated with very, you know, large particles potentially. So this event starts out cold and it gets warmer and drier. And this was that uncommon southwesterly wind mode that I pointed out Era 5 cannot capture in Kiruna. And it's associated with those mountains. So we have some topography southwest of Kiruna that we don't see southeast or north of it. And for our vertical profiles, we're seeing a pronounced temperature and relative humidity inversion, and it's drier, you know, than the other events. So we're seeing these dry layers. Great. So this is our summary of the types of events, the types of cases I've shown you here in Kiruna. So we have a deep event that lasts quite a long time, 20 hours at least, or 20.51 hours. Substantial, some accumulation associated with it for liquid water equivalent, 5.12 millimeters. We have high radar reflectivities. We see a structure in the 2D histogram, narrow range of Doppler velocities. And with this event, we had northerly winds and it was cold. And in the vertical profile, we see a moistening of the boundary layer through the free atmosphere. And it was associated with that weak low pressure system. For our shallow event, it lasted over 40 hours. Barely anything accumulated, very dry, not very much going on. And through the radar, we saw we have low radar reflectivities, invariant Doppler velocities, all 0.5 meters per second falling towards the radar. We have the northerly winds, so we're considering cold air advection. That is associated with this persistent high pressure. And there was a strong temperature and relative humidity inversion. For this intermittent case, it lasted 76.3 hours. It was an extreme deep low pressure system. We had substantial amounts of accumulation for this region, 12.32 millimeters. We saw high radar reflectivities, an increase in Doppler velocities closer to the surface, so maybe aggregating particles, yeah. Southeasterly winds, a common wind mode for this area. Moistening of the boundary layer in free atmosphere. I mentioned the deep low pressure. And then for our virga case, lasted 3 hours, about 0.22 millimeters of precipitation, liquid water equivalent. We had that very high radar reflectivities aloft and the low radar reflectivities near the surface. We had southwesterly wind, which is that uncommon wind direction, and it was cold and dry. We saw temperature and relative humidity inversions for this case, and we saw a sort of weak low pressure system north of Scandinavia. So I've shown you some snowfall events and we've looked at what are their properties, and what I'm going to do next is just compare these sites in a slide. So in both regions we saw deep, shallow, and intermittent, and right now I've redefined something and I'm going to let you in on what I've done here. So we're redefining this pulsed case is an enhanced snowfall. So let me, so with this intermittent, both of them we saw on and off precipitation at the event, at the sites, but Haukeliseter has more pulsed nature because of orography affecting and enhancing these precipitation events with these updrafts and upward motions. Both of them saw deep snowfall events that were associated with weak low pressure systems and substantial liquid water equivalent. Both of them had shallow cases, persistent high pressure, low liquid water equivalent accumulated. And I mentioned the intermittent being at both and the pulsed being an enhanced version of the intermittent. And this virga is very unique to Kiruna, where we see this low pressure. We saw low pressure from the north and low liquid water equivalent accumulated in very dry air. Something a caveat I want to point out is when I say high liquid water equivalent or substantial, I'm not comparing necessarily Kiruna and Haukeliseter, because liquid water equivalent is in all these cases is higher than in Kiruna because Kiruna is drier and cooler, so there's less accumulation there. So let's revisit those research questions that I showed you at the beginning of this talk. So, how are snowfall events influenced by their environment? Do we see synoptic scale weather patterns and how topography might influence the snowfall in an area? So yeah, we're seeing that there are specific cases associated with specific synoptic scale patterns. So we're seeing deep low pressure systems and types of storms, and high pressure systems over a region and how that might affect it. We're seeing orographic effects through the Doppler velocity and the pulse nature in the radar. And then in Kiruna specifically, we're seeing how dry layers and cold air advection may play a role in promoting different types of snow regimes. So how do these snowfall regimes vary across the distinct regions? Well, we're actually seeing that there's common properties between snowfall types in both Kiruna and Haukeliseter. And that's with the synoptic scale patterns associated with the events. And some properties that make them distinct and unique to those areas are these orographic effects, again, in Haukeliseter that would affect snowfall, and also the dry environment in Kiruna. So for my future work, I'll be continuing to look at instrument data that was taken at these sites, specifically using a video distometer called the PIP, it's a particle imaging package, to look at particle size distributions. I mentioned that the micro-rain radar gets a spectrum width, and I haven't analyzed it here with you today, so I'll be continuing to look at that. I'll look at back trajectory analysis to see where these parcels travel through and get an idea of moisture transport. I want to statistically define the regimes that I have qualitatively shown you, and understand what are the, in the context of climate, how anomalous are these events. I'd like to continue looking at these locations in snowfall using satellite observations, and also work with collaborators in Utah to look at snowfall accumulation. So if you are very excited about what I've shown you here today, we actually have our data available to look at in quick looks on a website. So we have reanalyses products, the radar, reflectivities and fall speeds, and then the data that I will be looking at soon is particle size distributions and particle densities. In addition, we have our surface meteorological measurements, our temperature, relative humidity, and winds. And then we have some satellite observations on here too to look at. Yeah, so with arrows. All right, so I'd like to acknowledge some people that I've been working with these last few years, or these, I guess, almost 2 years in fall, to work on this project. So I'd like to thank my advisor, Tristan Lequier. I'd like to thank Claire Pedersen. I'd like to thank my master's thesis readers, John Martin and Steve Avarice. I'd like to thank Pete, AOS staff, Sue, Chelsea, Sonia, and Dee, research group, and particularly the polar subgroup, my partner, James Wiepelman, my sister, Tessa Shates, and family, friends, and mentors that have all been very helpful and supportive of me as I work through my research. So thank you.
Great, so we have time for questions. Martin?
Yeah.
Yes, really intriguing, Julia. Really excellent. I'm imagining, how many years of data do you have at some of these stations?
So we don't even have full years of data.
Okay.
So we have just about a winter at each location, and they're not overlapping winters.
Okay.
Potential, hopeful future for more
But
data.
even in one winter, you're going to have
Right.
visitations by these various types of disturbances that propagate these modes.
Great.
So if you were to create a whole long time series at each station of especially the histogram, the really nice
Right.
taking the time out of the histogram for little segments of time, would you be able to create like a self-organizing map, display of the various modes of precipitation that you get at that location, and then that would give you a calendric listing of when those various modes occurred, and then you could see without taking a peek ahead of time
Right.
whether or not synoptic patterns fit what you identified in individual cases.
So I would like to do that. So looking at just the histograms, you can see that there's that defined structure, and I
Right,
guess
yeah.
probably take some kind of cluster analysis, which I'm interested in learning maybe, to kind of see, if we have refined structure, this defined structure, then it's synoptic. If we have broad, defined broad some way, then we have more of a pulse, thinking of Haukeliseter.
Right.
Or shallow. I think what makes it more confusing is the role of Doppler velocity. So we can't use the same definition for both Kiruna and Haukeliseter if Doppler velocities are, if we have this pulse and it not being exactly the same, the properties being different. So I think that there probably is a way to do it, which I'd be interested in learning. Like that's something that with defining regimes that I would want to do is like
Yeah, because it would
Alright.
give you a chance to do a blind assessment of
Right,
whether or
right.
not your categorization seems to fit
Right.
most of the time.
Right,
you
and
know?
then compare it to the synoptic
Right,
scale
exactly.
and be like, all of these are, you know, high pressure systems, and then go check them, and then they are.
And then they are, right, that'd be really
right.
neat, yeah.
That would be, yes, I would like to do that, we'll see, maybe. Yes.
Does the west coast of Norway experience atmospheric rivers? And
Yes.
Was that Erd one of them?
I think it was, so it was
That was phenomenal.
extreme,
There's
yeah,
like 3 separate atmospheric rivers.
yeah.
It was what?
3 separate ones that are
Really?
relevant hit.
Oh,
Right.
wow, okay.
Yeah, yeah, there was, on that figure, there's also the geopotential height contours overlaid, so you can see that tight gradient too, just bringing
So you can somewhat separate the orographic effect from the broad scale moisture transport that way if you looked at
Mhm.
integrated water content or something like that, right?
Right, right. I think that that's something that people within our group are looking at is, you know, looking at satellite observations just to study moisture transport into that area. Although that's not exactly what I'm doing. Mhm.
I don't know if I'm next. No.
So maybe?
Sure. Oh my God, I have so many, I just forgot all of them.
One question.
Okay, so one, like, do you know that for the data you have, like, how frequent each type of event was? Because, like, you look at one, the
Right.
deep synoptic, like, produces a lot more, like, reflux, something that like, a
Right.
decision manager would want to know, like, which events.
Yeah,
get the
so
most
just from what I was looking at, just qualitatively looking through it, for Haukeliseter, these pulsed events were dominant. So there's a lot of them. So the entire month of December is westerly winds, basically. So that's just pulse, pulse, pulse. We have a lot of liquid water equivalent accumulated for that. For Kiruna, I don't know if I stressed it enough, but virga stood out a lot. So there's a lot more cases of snow virga according to the radar. It's a little bit harder to tease out if that deep snowfall or if the intermittent snowfall occurred more often, and I think I need a more rigorous way to define them also, because it's not like there's a wind direction that defines them to be like, yep, westerly, it's this, you know. But, so I would say virga is really, you know, stands out, but that's not a lot of accumulation, so maybe policy people would be kind of like,
Yeah.
Yeah.
Like if they want to know in the future what's going to happen
Right.
based on which type's going to change.
right. Also, something that unique about this winter is that December is particularly warm for Haukeliseter, so that could be linked to the conditions associated with that December, and it's you know, not necessarily representative of the climatology. So maybe every year to year you couldn't say that it's that pulsed.
How ubiquitous do you think these regimes are beyond just your 2 stations here?
It's hard to say because I've only looked at these 2 stations, but I first started looking at Haukeliseter, and I had an idea of how Haukeliseter looked, and then I looked at Kiruna, and I was surprised because I was like, wow, we're seeing the same deep snowfall, and then I was even more surprised because the intermittent didn't have the pulse nature, and I was like, but so I was surprised at first to see them, you know, so similar, especially because, you know, that 1,000 kilometers apart, California scale. So maybe it is more ubiquitous, you know, in these high latitudes than we know. And that's part of doing this type of research, is also seeing what is there according to the radars and stuff.
John,
Yeah, a lot of good questions too that make me think about some other ones. But I wonder about this virga category in Kiruna. Is that maybe related, if you were to look at, you know, T-minus 2 days on all of those virga events, is that related to one of these moisture transport events on the southern coast of Norway? Because you've got the roof of Norway and the boundary between Norway and Sweden for subsidence that might just cut out the lower 2 kilometers of the
Right.
precipitation, and the rest of it looks the same as something that's happening
So-
further to the southwest.
I think that's definitely possible. The way I've identified precipitation, it's radar reflectivity is reaching this 300 meters above the surface. So with a lot of the virga that I didn't look at, there's nothing reaching the surface.
Yeah, okay.
So it's possible that for hours before we have a snowfall event, there's some virga, you know, happening before it reaches the site, and I just
Okay,
haven't
yeah,
identified
yeah,
it yet.
okay. I see what you're saying, yeah.
So it's definitely possible.
Okay.
what was your wind direction? Was it southwest?
So that was
Southwestern, yeah.
southwesterly, but I
So,
also
yeah.
have a virga case that's northerly.
Oh, that's interesting.
So
yeah.
the winds don't necessarily define the types in Kiruna the way they do in Haukeliseter.
Okay.
Well, we have talked a little bit about as that mountain range that Julia pointed out,
Yeah.
as winds go over that, we might have this subsidence that's kind of cutting out some
Yeah, that's what I'm
dry air.
wondering if that
And there's
doesn't.
some other stuff, and she's thinking of ways to do like a virga analysis as opposed to
Mhm.
research.
Yeah.
Yeah.
Yes, Mark.
Yeah, I just wanted to encourage you, Julia, to, even though you only have 2 point sources and you only have maybe one winter at each, since you have all these environmental conditions associated with these events, you can use this as an analog, use something like CloudSat, to look more globally at whether those conditions for CloudSat observations have the same as yours you see,
Right.
especially when we're looking at biases in the CloudSat snowfall estimates. I think these are really important
Yeah.
data sets. So
That's-
there is a way
Right,
to
right,
convey
right.
results.
Yeah,
more globally.
and that's something I'm definitely interested in for future work, is expanding to look at CloudSat Calypso and also passive sensors. Yeah, it's interesting.
Have you noticed, how frequently do storms that are affecting the first
Haukeliseter?
station?
Yeah.
Yeah, that one, affect the second station? How frequently are they, like, the events impacting
Right.
both stations? And then for those that do impact, is it a similar regime that you see with both stations?
That is an amazing question that I wish I could answer, and maybe looking at satellite observations could help, because our 2 winters are different years. So even if I see that the low pressure is, if it starts at Haukeliseter and it, travels along the coast or something, I wouldn't have data to verify it. So I could look at the maps and be like, we have a low pressure system, but I don't have data for it. So that, yeah, looking at surface satellite observations could maybe give some insight on that. That's a great question.
Are there any practical applications for weather forecasting you can think of for these findings, or is it really more basic research?
So for what I'm doing specifically is more basic research, but I think for weather forecasting and needing, it is a big deal to know, how much snow would we have with this event, and forecasting snow and observing snow is still challenging, and there's some uncertainty. So I think knowing more about the environment and the way the environmental conditions affect snow should help. I don't know how it would be used. That would be a different area, not in the scope of my work, but I think it should be useful. Whether or not basic research like that is used is a different question, I think, that I don't know the answer to.
Any questions? Mark?
This is unrelated to meteorology.
Okay.
Can you confirm that the UC Irvine nickname are the anteaters?
Yes. Zot.
Wait, what?
We have this hand symbol when we say zot.
Zot? Okay.
Thank you.
It's like that and the banana slug you see
Yeah.
Santa Cruz. Both interesting mascots. So, yeah. All right, let's thank Julia. Oh, sorry, great.
Yeah.
I can't help but think that the pulsing storm you're talking about must be conditionally unstable. Have you
Oh.
looked at that?
No, that's a very interesting question. It's definitely out of the scope of what I do, but maybe we can talk more about it, and I can learn a little bit about that too. Yeah.
Great. Let's thank Julia again.